function gonna work? Don't understand. Every day. We'll do it this way. All right. Almost not in place. It should be at all. All right, all right. I might activate over here. Go ahead and I imagine we would cover the practice of midterm for Chan's class first because you all have midterm tomorrow. And then assuming we have time, which we probably will, we'll look at the ones for no, which I'm sure will be more challenging because that's just the luck of the draw. Sometimes you get the easier teacher, sometimes you get the harder teacher. So let's take a look here. Here's the first couple questions. And as usual, feel free to ask questions about these questions if you got questions. I'll remind everybody that when you take your test on Wednesday or on Friday, make sure you read the questions carefully. It's a really important thing to do. It takes not a lot of time, but if you don't do it, it's really easy to approach this the wrong way. So we got this function. It's x squared times sine of 1 over x when x is not 0. It is 0 when x is 0. First, we're asked to show that f prime of 0 is equal to 0 using the limit definition of the derivative. So I'll point out, we're not using the general limit definition. We're not going to say that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. We're going to do f prime of 0. So it's going to be the limit as h approaches 0 of f of 0 plus h minus f of 0 all divided by h. Also, for those of you in No's class, if I remember, I will try to post this practice exam on Canvas so you can check it out on your own as well. So now we're going to plug this in. So we're going to write this as the limit as h approaches 0. F of 0 is 0 by definition, right? We have defined when x is 0, f of 0 is 0. That part's going to be 0. F of 0 plus h, well, h isn't 0. So f of h is just going to be equal to h squared times sine of 1 over h. So we're going to get f of h. It's an h, believe it or not. You might even write the minus 0, although I don't think you really need to write that. All divided by h. We're going to simplify. This is going to look like the limit as h approaches 0. H squared over h is just h times sine of 1 over h. This might feel like a sine of x over x sort of situation. It's not. Because if it was a sine x over x kind of deal, that limit would have been equal to 1. We know we're trying to get 0. This is a squeeze theorem situation. So we're going to say, great. Sine of 1 over h has to live between -1 and 1. But then I want h times that, so I'm going to multiply everything by h. So negative h is less than or equal to h times sine of 1 over h is less than or equal to h. And then we're going to take the limits of the outer parts. We know that the limit as h approaches 0 of negative h is equal to 0. And the limit as h approaches 0 of positive h is equal to 0. So by the squeeze theorem, the middle part has to have a limit that's also 0. So by the squeeze theorem, the limit as h approaches 0 of h times sine of 1 over h must equal 0. And I'll write, again, that was our f prime of 0. So we showed the derivative at 0 is equal to 0. Sometimes when it's this kind of problem, like if this was like an absolute value function or an absolute sure. Another common example here would be something like f of x equal to x times the absolute value of x. And you show that that function is differentiable at 0. This one you'd have to do the one-sided limits, like the right-hand side and left-hand side, to show that both sides are the same. This is not that case, right? We don't have to look at the two-sided limits because it's the same thing on either side of 0. So yeah. All right. Questions? I think the second part comparatively is relatively straightforward. We're just asking you to take the derivative when x isn't 0 because it's not differentiable at 0, I'm guessing. I guess it's not, I don't know. I guess it's not differentiable at 0, or we're not trying to worry about it, I think is more the point, really. So our function is, looks kind of blurry. Our function is x squared times sine of 1 over x. I would probably rewrite it as x squared times sine of x to the negative 1. So that then I can take the derivative using the product and the chain rule. So my derivative is going to be the derivative of x squared multiplied by the other piece left alone, sine of x to the negative first, plus, switch it up, leave the x squared alone. The derivative of sine of something is cosine of that something, multiplied by the derivative of the inside. The derivative of x to the negative first is -1 times x to the negative second. And since the problem doesn't say anything about simplifying, I would leave it as is. Actually, I would go back and look at the cover page and see if there's anything that makes me think I should do anything else. Close book, no calculator, don't turn the page over, show complete solutions, earn full credit. Academic code of conduct doesn't say anything about simplifying at any certain point. So I'd probably leave it like that. If I had time at the end of the test and I had bothered to notice that I could simplify this a little bit, I would maybe simplify it and write it as 2x times sine of x to the negative first, or 1 over x. And then the x squared times x to the negative second just ends up being x to the 0th, which is 1. So that ends up being a minus cosine of x to the negative 1. Because again, the x squared and the x to the negative second multiply to 1. Or you can think of it as x squared divided by x squared. All right. Question? How do you know when you Good question. Very good question. So we don't always know to use the squeeze theorem, but a good kind of clue that you might need to use the squeeze theorem is you have sine or cosine, and the insides are kind of going to infinity. So like here, right, sine of 1 over h, since h is going to 0, 1 divided by h is blowing up. And sine or cosine, something is blowing up. Well, if you think about sine or cosine, as you go out to the right, they just keep oscillating. So they don't have a limit that really exists. They don't get closer and closer to something. So that's how I typically know I need to use the squeeze theorem, is that if you've got sine of something and the argument's just getting larger and larger and larger, or negatively larger and larger and larger. That's kind of my clue, because I don't know what this piece is doing, right? It's just bouncing back and forth, back and forth, back and forth forever and ever and ever. But I do know It's stuck between -1 and 1. Now, just as a quick aside here, if this question had been slightly different, and I don't really know exactly how you do this, but let's just say this question happened to ask us, just for the sake of it, also tell me what is the limit as x goes to infinity of this function. Let's say that was the question. So then we're dealing with, I don't know, fine, it'll be fine, James. Sure. Let me make sure it's really going to be fine. Let me think for a second here. Nope, that's not work either. Fine, I'll do this. That'll be fine. Let's find the limit of f of x divided by x, just for the fun of it, just to illustrate a point, really. So if I asked what this limit was because I felt like asking it, then we start off by just writing it out. We'd have the limit as x goes to infinity of x squared times sine of 1 over x divided by x. We'd simplify. We'd write it as the limit as x goes to infinity, x squared divided by x is just x times sine of 1 over x. And this is not an example where I use the squeeze theorem, because the inside of the sine function, it's not going to infinity or going to negative infinity. The inside, or the argument of the sine function, 1 over x, as x gets really, really big, 1 over x gets closer and closer to 0. So this is actually the case that I was kind of alluding to earlier. Well, I could rewrite this as the limit as x goes to infinity of sine of 1 over x divided by the reciprocal of x, which is 1 over x. And then we can say that that limit is 1, because it's sine of something over the same something, and the something is going to 0. Which I know feels kind of like we're not showing a lot of work there, but you don't really have a lot of recourse. If you really wanted to like show work here, I don't think you need to do, but if you felt like you needed to, you could do this kind of like substitution thing where you're like, well, I'm going to say let y equal 1 over x. Then if x is going to infinity, y is going to 0, and I can rewrite this limit as the limit as y goes to 0 of sine of y over y. And then you might feel more comfortable saying that limit's equal to 1. You don't need to do that at all. But some people like to do that for reasons that are beyond me. But it's perfectly fine to say this is what it is, because you have sine of a thing over the same thing, and that thing is going where? Where's the inside part going to? 0, right? They both have to be going to 0. Sine of the thing over the same thing going to 0 means the limit's going to be 1. So that's just to kind of contrast where you wouldn't use the squeeze theorem. If the insides are going to 0 or some finite number, we don't usually think about the squeeze theorem for sine or cosine. But if you have sine or cosine, specifically those two, and the insides are getting infinitely large, that's when you use the squeeze theorem. Or at least that's when I think about using the squeeze theorem. But the bigger answer is there's not really like a well-defined process for when you use the squeeze theorem. So I know it's not a great answer, but it's the best answer I got.
So when the sine, the inside is 0.
Nope, not 0.
Infinity.
Or negative infinity.
Is the squeeze theorem only applied when this thing approaches to 0?
No, but that is often the case. For example, we could have added 4 to each piece of this function. And then the limit would have been 4. And you still could use the squeeze theorem in the same way, right? If you go back to the example here, and I just like slapped on a +4 to everything here, +4 here, +4 there, +4 there, and then my limit would end up being, it would have been 4, because it would have stuck between 4 plus 1 over h and 4 minus 1 over h, and that both of those are going to go to 4.
No, but what I mean is, like, let's say you would have added +4, you would have still taken the limit as h approach 0.
Right, because that's what we're being asked about, yeah. Because we started off, right, with f prime of 0 being the, right, we're using, how did we get this limit as h approach 0? What made me do that? Right, the definition of the derivative. That's why we're taking the limit as h goes to 0 here. But often It is that. It's not always that, but yes. A lot of the time when you're using the squeeze theorem, it's going to be because h is approaching 0, but not always.
Can you use these theorem and take the limit as change approaches?
Yep, totally, yeah. For example, in fact, you all should try this one right now. The limit as x approaches infinity of 3x plus cosine of x divided by 2x plus 1. I want you all to try this, really, like get out a pencil or whatever, and start with cosine is between -1 and 1. And then I want you to manipulate the middle part so it looks like that. And then take the limit of both sides. I give you a minute and a half. I'll even write the next step for you. I don't love how I wrote that. I'm gonna write it again. All right, been a minute and a half. So I started off by adding 3x to everything, totally valid. And then I'm going to try to make the middle look like the thing I'm trying to take the limit of. So I'm going to do what? Divide everything by the appropriate denominator, 2x plus 1. And then, now that the middle part's looking like the thing we're trying to take the limit of, take the limit of the boundaries, of the outer things. So we're going to take the limit as x approaches infinity of 3x minus 1 over 2x plus 1. And here I wouldn't show more work. Like there's this whole process of dividing by the highest power of x, or we can use the shortcut that says if the degree on top and the degree on the bottom are the same, the limit is the fraction of those leading coefficients, which is going to be 3 over 2 in this case. And also, the other one is also going to have a limit that's 3 over 2. So limit as x goes to infinity of 3x plus 1 over 2x plus 1 is also 3 over 2. So it has to be true that by the squeeze theorem, the limit of the middle part as x goes to infinity must also be 3 over 2. There's another type of squeeze theorem question that could get asked. I would ask that question, yes. Or something similar to it. So I'll say it again. The way you know you might, and again, it is might, but it's a pretty good might. The way you might know you need to use the squeeze theorem is you have a sine or cosine, and the argument is approaching infinity or negative infinity. I can't say more than that, really. That's all there is to say. That's the only time I ever really know to use the squeeze theorem. Or they tell you to blatantly. I don't know how you do this problem unless you use the squeeze theorem. You can't really do it. Whoa. 3 times infinity divided by 2 times infinity is not necessarily 3 over 2. So I want to back up for a second and say infinity divided by infinity, you can't just assume it's going to be what you think it's going to be. No, you cannot. It's what's called an indeterminate form, and just like a 0 over 0 limit, right? 0 divided by 0 doesn't equal 1 necessarily. Infinity divided by infinity doesn't equal 1 necessarily. What it really means is you have to do more work. Even though it might end up being what you think it's going to be, you have to do the work to show it. Okay, let's move on. So, on to question 2 on this practice exam. Some derivatives. So here's what I'll say about derivatives very generally. It's usually a good idea to simplify first if you can, or at least rewrite it in a way that makes it easier. Square roots are never the way I want to write this. So I'm going to rewrite this as plus u, the derivative of, plus u again, secant of x plus x to the 1/2 to the 1/2. All right, that just makes it easier for me to handle it because I know I can use the power rule. Also, I would point out, if you're just rewriting it, you should say you're still taking the derivative, or you shouldn't say this is f prime. You say your function f of x is this. Not a huge deal, but some people are nitpickier than others. So I've got a chain rule. I got a couple chain rules here. I've got secant of some stuff. So my outermost function is secant. So the derivative is going to equal secant's the worst, right? Secant of the stuff times tangent of the stuff times derivative of the stuff. Only for secant and cosecant and inverse secant and inverse cosecant does the stuff show up twice, right? Any other function where you're using the chain rule of stuff usually only shows up just the one time. So you're going to have secant of x plus x to the 1/2 to the 1/2 times tangent of x plus x to the 1/2 to the 1/2 times the derivative of that inside part. And depending on how much writing you want to do, you might just write the inside part prime. Normally I wouldn't do it this way. Normally I would actually just take the derivative, but for now I'm just going to say I'm going to do, 1/2 James, and then prime. So I have the secant of the stuff, tangent of the stuff, and I still have to find the derivative of the stuff. The downside, if you take this extra step, is then you have to write this part again. So I probably wouldn't actually recommend doing it that way, but I want to show you the steps. I still have secant of x plus x to the 1/2 to the 1/2 times tangent of x plus x to the 1/2 to the 1/2 times, okay, I've got some new stuff to the 1/2 power. The derivative is 1/2 times that new stuff, x plus x to the 1/2 to the negative 1/2. And then we have to use the chain rule again. I said new stuff. I have to multiply by the derivative of that new stuff, which is going to be 1 plus the derivative of x to the 1/2 is 1/2 x to the negative 1/2. And you really, really have to have parentheses around that. Otherwise, it's not going to be exactly correct. Well, that's a little ugly. Not the worst thing I've ever seen, but nice, right? Interesting. Okay, if you have questions, ask them. If not, I'm just going to keep going. So next one here I see is a product rule, x times e to the negative x squared. I will point out this could have been written as the derivative of x over e to the positive x squared. If it was written this way, you could do it as a quotient rule, or you could choose to rewrite it that way and do it as a product rule. Either way is legitimate and acceptable. But since it's already written this way, I probably wouldn't change it back to that. I would just do it this way. So product rule, the derivative of x is 1, leave the other stuff alone, plus, switch it up, leave the x alone, the derivative of e to the negative x squared, or e to the stuff, is going to be e to the stuff times the derivative of the stuff. So we're going to get an e to the negative x squared times the derivative of negative x squared, which is negative 2x. I don't like a times the negative without a parentheses around it, so I think you need a parentheses right there. I wouldn't write anything else. I would just say, there's my answer. In fact, that's also this is. It is a good idea to indicate where your final answer is. It makes it easier for the person to see what they're trying to grade. Should also show your work, right? Okay. I wouldn't simplify this, right? We're not trying to simplify, even though you totally could simplify this. We should not. The instructions don't say anything. All right, look at this gross thing down here. There's a hint there, even though they didn't say it. The hint is that looks gross enough. but there's a bunch of stuff multiplied and divided together that they're telling us without telling us that they want us to use logarithmic differentiation. For sure, like without a doubt. No one wants you to do this the long way. At least I don't actually know that because I didn't look at the solutions, but that is certainly something you could do and probably are expected to do here. You could go the long way, but it's terrible. So what we're going to do is we're going to say, great, we're going to write it as y equal to all that stuff, 2x minus 3 times, I'm going to write that as 3x squared plus 4 to the 1/2 divided by e to the x times sine of x. And I did myself a favor. I left myself some space in front of it there so I could throw in a natural log. So I'm going to take the natural log of both sides. And the whole reason for doing this is so that you can break up the right-hand side into easier pieces by using the log rules for products and quotients. I think we should do this next step in, I guess, 2 steps. Here's how I think we should rewrite this. Natural log of y equals, okay, every factor on top gets a positive logarithm in front of it. Every factor on the bottom gets a negative logarithm. So it's going to be the natural log of 2x minus 3 plus the natural log of 3x squared plus 4 to the 1/2 power minus the natural log of e to the x minus the natural log of sine of x. Natural log of the top minus natural log of the bottom, and then the natural log of the top breaks up into those 2 pieces, and the minus the natural log of the bottom breaks up into those 2 pieces, but the minus sign distributes to both of them. And then we should do one more thing before we differentiate. We should bring down any of the powers. So we have natural log of y equals the natural log of 2x minus 3 plus 1/2 times the natural log of 3x squared plus 4 minus the natural log of e to the x is just x, and then minus the natural log of sine of x. And now we're ready to differentiate both sides. Derivative of natural log of y is going to be 1 over y times the derivative of y. And then the right-hand side, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. So here we're going to get 1 over 2x minus 3 times 2 plus 1/2 times 1 over 3x squared plus 4 times the derivative of 3x squared plus 4 is 6x minus 1 minus 1 over sine times the derivative of sine, which is cosine. I'm not done yet, though, because I still have to write my answer with the y brought over to the other side. I really, if you're trying to save yourself time and space, this is definitely a place where we shouldn't write this in 2 steps. We should write this in 1 step. Meaning, when we bring the y over here, we're not going to write it as y. We're going to write it as the terrible 2x minus 3 times 3x squared plus 4 to the 1/2 over e to the x times sine of x. I know it's kind of awful, but it is what it is. This is kind of a terrible problem. If I were to assign a problem like this on the test, I would have written it as just the natural log of all that stuff to start with. So you don't have to do this whole process of taking the log of both sides and then doing 1 over y times y prime and bring it back over.
I remember the problem.
Sure, so we'll do it that way as well. Right, exactly. That's why you don't want to do it that way. You can do this using the quotient rule, the product rule twice, and the chain rule once. I don't want to do all that. This is easier, I think. So at the end of the day, we have y prime equal to our y. Now, here's what I would say, really. If I was short on time, or knew I was going to be short on time, I would just write y. I would say, hey, it's y times, and actually I might simplify this because it's easier to write. I might write this as 2 over 2x minus 3, and 6x over 2 is 3x over 3x squared plus 4 minus 1 minus cosine over sine is cotangent of x. And if I was short, and then I might even, to make it more obvious that I knew what I was doing, be like, hey, cool, there's my y, and draw an arrow pointing there. I would give full credit for that. I can't guarantee your teacher will, but it shows you know what you're doing, and you just didn't have the time to write in what y actually was, which is super rips. And then if you really have the time, you can cool y prime is I really don't want to write it, but I'm going to 2x minus 3 times 3x squared plus 4 to the 1/2 over e to the x times sine of x times all that. I might do that though. Usually people are pretty forgiving in that way because they're like, well, yeah, they know what they're doing. They just didn't have the time to write it out. But okay. I do recommend though, when you're going from this step to this step, I do think it's actually worth your while to simplify the expression because it's just less writing.
So you get it.
This looked like a lot of things multiplied or divided together. So I had a factor, a factor, a factor, a factor. And there wasn't anything else. There wasn't like a plus something somewhere. Like it was just one kind of fraction with things multiplied together in the top and the bottom. That's kind of the clue that we might want to use logarithmic differentiation. Again, you can totally do this without doing it this way, but it's gross. Right? It's sorry, no, it's not. It's just the derivative of all this, which is the bottom times the derivative of the top, and the derivative of the top, you have to use the product rule, the product rule and the quotient rule, minus the top times the derivative of the bottom, where you have to use the product rule, all divided by the bottom squared, which is, yeah, it's not great. It almost feels like not enough room to do that problem, but we made it. Okay. Let's move on to the next question. Let's read it carefully and slowly. Suppose f of x equals the square root of x squared minus 1. Find the equation of a tangent line that passes through 1/2 comma 0. I appreciate the notice here. Notice the point 1/2 comma 0 does not lie on the graph. So right, it's a very different question. If the point's on the graph, you're just saying, okay, that's my point. You're plugging in that point to find the slope of the tangent line, and then you're using that point and that slope to find the equation of the tangent line. But if it's a point not on the graph, it's a totally different animal. So I would probably draw it. Interesting. Okay, maybe. Yeah, I guess. Interesting. Sure. Yeah. Yeah. So I can see that since the square root of x squared minus 1, we need x to be bigger than or equal to 1. Technically, there's more to it than that, but I'm going to save that until the end so we can. I blame you. No. Why? Okay. So I'm just going to pretend like I don't really know what this graph looks like. It's kind of like that. Maybe. There's my. And then we're trying to find. That's 1 comma 0. And then there's my 1/2 comma 0. And we're trying to find the equation of the line tangent to our function that goes to that point. So maybe it's something like that. Okay, we've done problems like this a couple times. The whole crux of this is writing what the slope is equal to in two different ways. Using the slope equation, y2 minus y1 over x2 minus x1, and using the derivative. And we need to give this point a name. For whatever reason, we usually call it a comma f of a. That's just standard process. I don't know why. But it always feels wrong to use x comma f of x. It just is. This is a comma f of a. But then we should actually write what f of a is. That's a comma square root of a squared minus 1. Okay. So now, find the slope two ways. So the first way, let's just do the difference in the y's, difference in the x's. So it's y2 minus y1 over x2 minus x1. So that's going to be, so square root of a squared minus 1 minus 0 divided by a minus 1/2. Okay. Seem good? I mean, relatively speaking. Let's find the slope using the derivative. So my function, f of x, is x squared minus 1 to the 1/2 power. F prime of x is going to be 1/2 times x squared minus 1 to the negative 1/2 power times 2x. And so then our slope is going to equal f prime of a. And I'd probably simplify a little bit here. I'd probably cancel the 2's and write this as x over x squared minus 1 to the positive 1/2. Or plugging in a over the square root of a squared minus 1. Now what do we do? What's that? We're not there yet, but that's where we're gonna go eventually. We have to find A. How are we gonna, why did we find the slope in two different ways? Right? We know the slope is this, but we also know the slope is this. These two things, this and this actually have to be the same. So we set them equal to each other, which allows us to find A, which allows us to find the point of tangency. So we're going to set the square root of A squared minus 1 over A minus 1/2 equal to A over the square root of A squared minus 1. I will point out this looks like a very well thought out problem, because when we cross multiply, the square roots are going to multiply together nicely to get just A squared minus 1. So we cross multiply, and we get on the left-hand side A squared minus 1. On the right-hand side, A times A minus 1/2. Multiplying it out, we have A squared minus 1 equals A squared minus 1/2 times A. The A squareds cancel. And we have -1 equal to -1/2 A. Multiply both sides by -2, we get 2 equal to A. Interesting. So now we can find the point. So the point of tangency is going to be A comma the square root of A squared minus 1. And A was 2, so our point is 2 comma root 3. And now we're going to use the point slope form. We're going to say, oh, I guess I should also find the slope. My slope is equal to, you can use either equation. I'd probably use that one. My slope is going to be 2 divided by the square root of 3. Just plugging in my A by plugging right in. So great. I've got a point. I've got a slope. I can use the point slope formula and say that y minus the y value, which is the square root of 3, equals 2 over root 3, the slope, times x minus the x value of 2. I will again point out the question does not say to write this in the y equals mx plus b form. I'm not going to take the time to do that. You shouldn't either. Unless it, especially with this one, which just looks kind of gross, but yeah. No, there isn't. Yeah, good. Yeah. Certainly you could ask a question like this, which would require implicit differentiation, although maybe not, because it's harder to find the slope in the slope equation sort of way. So actually, I think you probably couldn't ask a good question like this that was implicit as well. I'm mildly surprised that there isn't also a point on the left-hand side of this graph. So just so everyone knows, I didn't actually plot it, but just want to point out eventually, maybe never. Where'd you go? Sorry, challenges here. There we go. If you graph this, it has a left and a right side. If we graph y equal to the square root of x squared minus 1, it looks like that. So part of me was slightly surprised that we didn't find two tangent lines. One, the one we found that was like going through the point right there, going through the point 1/2 comma 0, and then one also over here. But I guess there wasn't one, I think. I can't see what we would have done, what else we would have done to have found it. So I'm relatively convinced, but if I discover something later when I'm thinking about it, I'll let you know. Yeah.
So if there were two, the question would be this.
So if there were 2 points of tangency, what's happened in previous problems we've done this is when we've solved for A, it's been a quadratic equation we've solved for, we've gotten 2 solutions. So yeah, typically if there's 2 points of tangency, you end up getting 2 solutions over there, but we didn't this time. Yeah, and I don't think I'm not thinking of something, but I suppose it's, maybe I am. No, I don't think so. I'm pretty sure, but I'll check it out later on my own, because I think we should move on. I think if you did this work, you'd get most of the credit on a problem like this, even if you missed something. But I'll go back and think about that, because there might be something else there. All right. Suppose 2xy plus xy squared equals 1. Without even looking at anything else, we know we're going to have to use implicit differentiation here. You've got x's and y's mixed up together. That's a key indicator that implicit differentiation is usually what's on the table here. But then we should read the question. Find dy dx. Okay, so yes, exactly that. So we're going to differentiate both sides. So we're going to use the product rule. I'm going to think of this as 2x as its own piece times y plus x times y squared equal to 1. And now we're going to differentiate. Product rule in both spots. So the derivative of 2x is 2. Leave y alone. Plus switch it up. Leave 2x alone. The derivative of y is y prime or dy dx. Whichever way you choose to write it should be fine. Plus, now we're going to do this part. Derivative of x is 1. Leave y squared alone. Plus switch it up. Leave x squared alone. Leave x alone. Take the derivative of y squared, which is 2 times y to the first times the derivative of y. Equal to 0. Make sure you keep thinking you're differentiating, right? I see so many people leave the right-hand side as 1 because they forget they're taking the derivative on both sides. Derivative of both sides, constants by themselves, their derivative is going to be 0. Now we're going to solve for dy dx. So all the terms that have a dy dx, make sure they end up on one side and everything else on the other side. It's totally fine to underline them. I'd probably leave them on the left. So on the left-hand side, I have 2x times dy dx plus, I'd write that as 2xy times dy dx equal to, bring the other stuff to the other side, so it's negative y squared minus 2y. Factor out the dy dx, so you have 2x plus 2xy equal to negative y squared minus 2y. Divide by the leftovers, so dy dx is equal to negative y squared minus 2y divided by 2x plus 2xy. Okay. To find where something has a vertical tangent, we need to figure out what? Where the slope is, that's a horizontal tangent, or the slope is undefined. In this case, that means where we're dividing by 0. So the question here really is, where is 2x plus 2xy equal to 0? And I can think of two values. And it'd probably be easier to see if I did some factoring. So if I factor out the 2x, I'm left with a 1 plus y. So either x equal to 0 or y equal to negative 1. Now, interesting. So I am curious how much your instructor thought about this question. But here's what I'll point out. So the answer to this question is not the point 0 comma negative 1. That's not the answer, right? We're saying you get x equal to 0 and whatever the y coordinate is, or y equal to negative 1 and whatever the x coordinate is. So let's look at x equal to 0 first. So if we look at back at our equation up here, if we plug in x equal to 0, what do we get? Well, we get 2 times 0 times y plus 0 times y squared equal to 1. There isn't a y coordinate. There's no solution. X equal to 0 isn't a point on this graph. I'll show you in a minute. So that's actually not going to be an answer to this question. All right, cross it out. X equals 0, even though it would give you a place where the function is undefined, or sorry, where the slope is undefined, it's not in the domain of the original expression, which is kind of weird to think about because it doesn't look like this thing has domain issues, but it does. Implicit functions are weird. Let's try y equals negative 1 and hope we get an answer. So y equals negative 1. Let's see, we have 2 times x times negative 1, so negative 2x plus x times negative 1 squared, which is just plus x equal to 1. And that's going to work out just fine. We're going to have negative 2x plus x, so negative x equal to 1, so x equal to negative 1. So to answer the question, find the coordinates in which the curve has a vertical tangent. The only correct answer is the coordinate where x is negative 1 and y is negative 1. Thank you. That's the only answer. That's a tricky question. I wonder if he meant it to be that tricky. Oh, and just to kind of clarify, just to verify for you all that that is what I said it was. So if you were to graph that implicit equation, 2xy plus xy squared equal to 1. Look, x can never be 0. You get a vertical asymptote as you get closer and closer and closer to x equal to 0. So that's why that's not one of the values. But over here, at -1, -1, you certainly would have a vertical tangent. Kind of cool. It's not a bad question. All right. Look for the next one. Oh, I don't know. Next one. Word questions. Oh. All right, let's just read it and see what we get. Suppose the circuit consists of 2 resistors connected in parallel. The total resistance R of the 2 resistors R1 and R2 is given by this equation. In the circuit, the resistor R1. Okay, so now we're about to read the important stuff. In this circuit, the resistor R1 is increasing at a rate of 9 ohms per second. Cool. So the rate of change of R1 with respect to T is 9. I guess you could write units if you really wanted to. I don't really want to. But you could write ohms. I don't know. There's probably a symbol for ohms. It's probably like omega or something. Great. I'm going to write O. And then the resistor R2 is decreasing at a rate of 18 ohms per second. So dR2 dt is negative 18 ohms per second. What is the rate of change of the total resistance? So they're asking us to find the rate of change of R. This is, in some ways, a very nice related rates question to ask in that they're not asking you to do a whole lot of setup, right? You don't have to find the equation relating the 3 resistances. They're giving it to you. Your job is to differentiate both sides of this equation. If it were me, I would start off by rewriting it as R to the -1 plus equals R1 to the -1 plus R2 to the -1. I'd much rather use the power rule than the quotient rule. So let's rewrite this as, I know I said that before, but I'm going to say it again. It is almost always a good idea to rewrite your equation or your function so that it's simpler to differentiate. Or in other words, simplify before you take a derivative if you can. All right, so now we're going to take the derivative, remembering that everything is a function of time. So that when we take the derivative and use the chain rule, these 3 things had better show up in my next equation when I take the derivative. So differentiating both sides, the derivative of some stuff to the -1 power is -1 times that stuff to the -2 times the derivative of that stuff. Same deal on the other side. The derivative of R1 to the -1 is going to be -1 times R1 to the -2 times the derivative of R1. Same deal for R2 to the -1. It's going to be -1 times R2 to the -2 times the derivative of R2. Okay, so we're trying to figure out what dr dt is equal to. That means everything else we should be able to plug in for. So let's see. dr1 we know is going to be 9. I should say dr1 dt is 9. dr2 dt is -18. They're telling us that R1 is 6. R2 is 3. But they didn't tell us what R is. And that is something we need to find. But we do have an equation relating R and R1 and R2. So to find R, you're going to plug in the values of R1 and R2. So 1 over R is equal to 1 over 6 plus 1 over 3 1/6 plus 2/6 is equal to 3/6, which is 1/2. So R is going to equal 2 ones. 2 ones? 2. It's 2, right? If R is equal to if one of R is 1/2, then R is equal to 2. So that's what we're going to get there. R is going to be 2. All right, so here's what we've got. So this is where I actually go back to so I don't really want to write 2 to the negative seconds. I want to write 1/4. So I have negative 1/4 times the thing I'm trying to find, dRdt, is equal to 6 to the negative second is 1/36. So negative 1/36 times 9 minus 1 times 3 to the negative second is 1 times 1/9. So 1/9 times negative 18. These numbers were picked with care. So let's simplify a little bit. Negative 1/4 times dRdt is equal to negative 1/36 times 9 is negative 1/4. And negative 1/9 times negative 18 is positive 2. And instead of making the foolish choice of adding this together, let's multiply both sides by negative 4 first. So I multiply both sides by negative 4, I get dRdt equal to negative 4 times negative 1/4 is 1, and negative 4 times 2 is minus 8. So dRdt is negative 7 ohms per second. Well, I would say your instructor is writing some good, fair problems. They're approachable, they're not too terrible, but they're certainly not easy. They're fair. All right. That's the last page. No, yeah, that's the last page. Questions, comments, concerns? I think this test, I should ask all you. How similar did you feel like his first midterm was to his practice midterm? Somewhat ish, kind of. So, I mean, to me, I would certainly study these things. Obviously, you should know how to take derivatives. You should know how to find the slope of a tangent line. You should know how to do implicit related rates. Yeah, that's what I would practice. In that vein, I almost hesitate to look. I haven't looked at the other instructors' practice exam because let's take a look and see. We'll try and cherry pick some problems that feel like they're not too terrible. Okay. Let's look at some of these examples for this. How's that? Oh, sorry, I'm missing this. Sorry, I'm like, how is this page 3 of 7? Because I hit the back page. Oh, yeah, he loves this kind of stuff. So here we have an example. Differentiate the function, the absolute value of x squared twice for x equal to 0. X not equal to 0. Okay, so what does the absolute value of x squared look like? See, I'm curious about this question because I'm pretty sure that if f of x equals the absolute value of x squared, that's the same as x squared. Right? It's just a parabola. So I don't think it's incorrect, although I feel like I'm going to have to check the solutions because I feel like I'm doing something terrible. I think it's perfectly correct to say that the derivative is 2x. We'll say more about this in a second. And the second derivative is 2. Let's take a look though. So let's say we were trying to be a little bit more obnoxious about it. If we write this way, right, the absolute value of x squared, you could say, well, piecewise function, the absolute value of x is equal to x if x is already greater than 0. Right? If something's already positive, its absolute value is just itself. But if the thing is already negative, you have to negate it to make it positive. So we could write our function as a piecewise function. And I'm really curious if your instructor meant for this question to be like this, or if he wasn't, I don't know. It just seems like a weird question to ask. So then finding the derivative this way, piecewise, let's see what we get. The derivative of x squared is 2x when x is greater than 0. The derivative of negative x squared is going to be 2 times negative x to the first times the derivative of the inside, which is negative 1, which, hey, that's 2x. Oh, so we were right. The derivative was 2x either way you sliced it. Okay. And then the second derivative is going to be 2. Kind of weird. I don't know. I don't get the point of that question.
Did you get chain rule?
I did. I did the chain rule for negative x squared. I said I could have also so that's an example where I could have simplified it first. I didn't want to because I wanted to show that we kind of get the same thing either way. But if you would simplify this first, oh yeah, negative x times negative x is just x squared. The derivative is 2x. Or don't simplify it. Use the chain rule. 2 times your stuff to the first times the derivative of your stuff. Either way, totally valid. All right, let us look at this next one. Ooh, twice. Wow, twice. I mean, twice isn't that bad. So our function is x to the fourth times cosine of 1 over x. And as I've said many, many times, I would always rewrite 1 over x as x to the negative first if I had to find its derivative. So I want to think of this as x to the fourth times cosine of x to the minus 1. Now, this is a good question. So let's take the first derivative. Product rule. 4x cubed times leave the other stuff alone. Add, switch, leave the first stuff alone. The derivative cosine of some stuff is going to be negative sine of x to the negative first times the derivative of x to the negative first, which is negative x to the negative second. And especially when you're being asked to find a second derivative, it is definitely in your interest to simplify this before moving on to the next step. There's not a lot to do with this first piece. You still have 4x cubed times cosine of x to the negative first. But the second piece, there's a lot of simplifying to be done here. One, a negative times a negative is a positive. But more importantly, the x to the fourth times x to the negative second, you can add those powers, and 4 plus negative 2 is just 2. So we're going to say that's x squared times sine of x to the negative sine of x to the negative 1. That's a lot easier to deal with. All right, so question? Not if I have to take the second derivative. So right, if you have to take a second derivative, sure, you don't have to, but I would rather not use a triple product rule when I can use a regular product rule. So definitely, if there is a second derivative there, you want to simplify your first derivative. It is your best choice. Okay, so then second derivative, we have to use the product rule twice. So we're going to get 12x squared times leave cosine of x to the negative 1 alone, plus 4x cubed. Now here's some good news. Some good news. We already know what the derivative of cosine of x inverse is. Excuse me. It's all that right there. Right, the derivative of cosine of x to the negative first was negative sine of x to the negative first times negative x to the negative second. So I just want to point out that if you've already done the work, you don't have to think so hard about doing that same work again. You can just be like, yeah, I know what that's going to be. I might even simplify it as positive sine of x to the negative first times x to the negative second. Right, multiplying the minus signs together. Plus, now, so we dealt with that piece, right? That's all that. Now we have to deal with this piece. So now the derivative of x squared is 2x times, we give the sine of x to the negative first alone, plus x squared times the derivative sine of x to the negative first is going to be cosine of x to the negative first times negative 1 times x to the negative second. And I would stop there. I would not do any simplifying, even if there was simplifying to do, which there is. I don't care. If they said to simplify, I would point out that this term right here, 4x cubed times x to the negative second is just 4x. And the 4x times sine of x to the negative first plus the 2x times sine of x to the negative first would become a 6x times sine of x to the negative first, but I'm not worrying about that. All right. That's the same page. Now to the page I was looking at before. Solve the following problem. That seems very general. Well, let's solve it. So, for y squared equal to 4x, use implicit differentiation to find the points where bless you, dx dy vanishes. What do we mean by vanishes? Right, that's what I would assume, where is equal to 0. So, this question, I think, is asked in a purposely confusing way. We're finding dx dy, meaning we're imagining x is a function of y, not y is a function of x. So y is like the independent variable and x is like the dependent variable. If it helps, and it might, you might write down, okay, I'm thinking x is a function of y. Here's the work I would do if I didn't. So there's two ways you can do this work. You can differentiate this, pretending like y is the independent variable. So our derivative for y squared equal to 4x is going to give us, the derivative of y squared is just 2y. End of story. The derivative of 4x is 4 times the derivative of x, which is dx dy. Or if you prefer, you could say, yeah, y squared equals 4 times some function of y. Differentiating both sides, we get 2y equal to 4 times f prime of y, which is the same as your dx dy. You can write it that way if it helps you think about what's happening. All right, so now what are we going to do? Well, we want to find where this thing vanishes. So we're asking, okay, great. Where does dx dy equal 0? Well, if I solve for dx dy, it looks like dx dy is equal to 2y divided by 4, or if you prefer, 1/2 times y. So what does y have to be for this to equal 0? It's got to be 0. And if y is 0, what does x have to be? Also 0. So kind of not very excitingly, 0, 0 is where this derivative vanishes. Yeah, that's all I want to say about that. Unless you have questions about that. Other than why is it so weird? I don't know why it's so weird. It's just weird. Okay, here's kind of a terrible question. If you were to think about what this meant graphically, what kind of tangent line would we have? It is a trick question. Because if you were thinking, well, the derivative is 0, so it's a horizontal tangent line, that'd be wrong. Because that derivative where it's a horizontal tangent line is how y is changing over how x is changing. If you flip it, you're really not thinking about how x is changing over how y is changing. So you're getting like 0 change in, oh my God, like you're getting like 0 change in x, meaning you got a vertical tangent line, not a horizontal tangent line when dx dy is equal to 0. It's kind of weird. It's kind of like dy dx is equal to 1 over 0. It's literally like you could flip both sides, but kind of strange. Okay, let's get away from the strangeness. For this next equation, for x squared plus y squared equal to 1, okay, when you read this, before you read anything else, we know that that equation looks like a circle. Use implicit to compute the normal line, meaning the perpendicular line. Show the normal line through a point x naught y naught on x squared plus y squared equal to 1 passes through the origin. Okay, so this question doesn't give you a point. All right, so it says compute the normal line. And if they say find the tangent line, specifically this is for nose class, he asked a homework question like this as well. If they say find the tangent line or find the normal line and they don't give you a point, you have to make up a point. And you're literally just calling it x naught, y naught, right? That's what he did right here. So here's my circle. Here's the point x naught comma y naught, where I'm going to find the equation of the normal line, the one that's perpendicular to the tangent line. We're still going to start off by finding the slope of the tangent line. So we have to find the slope of the tangent in the usual implicit way. We're going to take the derivative of both sides. So that's not too terrible. 2x plus 2y times dy dx is equal to 0. If this was a more normal question that was implicit, where they gave us an actual point, I would say you should plug in the point right now. Since they didn't really do that here, it's not really helpful to plug in x naught, y naught. It doesn't really make it look different at all. So let's just solve for dy dx like one normally would. So dy dx is equal to negative 2x divided by 2y, which is just negative x. So then slope of the tangent is negative x naught over y naught. And then everyone should be able to tell me what the slope of the normal line is. Sure, but I'm going to simplify that to just, well, almost, sorry, say that one more time.
2x over 2y.
Not 2x over 2y, 2y over 2x. Right, when you find the slope of the perpendicular, you change the sign and you also take the reciprocal. And I'm going to cancel those 2's. The slope of the normal line would be just y naught over x naught. So then we want to find the equation of the normal line. So it's going to be y minus y naught equals the slope times x minus x naught. How do you show that that line passes through the origin? Well, you plug in the origin and ask if it's a solution. So if you plug in 0, 0 for x naught, y naught, so plug in 0, 0 for x naught, y naught. Do we get a solution? Well, let's see. Sorry, apologies. For x comma y. X naught, y naught is the point. X, y is the thing we're plugging in for. Sorry about that. For x, y. So plug in 0 there and 0 there. Let's see what happens. On the left-hand side, I get 0 minus y naught. On the right-hand side, I get y naught over x naught times 0 minus x naught. Looks like it's going to work out. On the left-hand side, I get negative y naught. On the right-hand side, the x naughts cancel and I get negative y naught. That checks out. Kind of interesting. Oh, sorry, you can't see that. Sorry. All right. Yeah. So the question is, so first we found the equation. So this is our normal line equation. Right? We were asked to find the equation of the normal line through the point x naught, y naught. So we found the slope. And our point was x naught, y naught. So we did y minus the y coordinate equals the slope times x minus the x coordinate. And then the question was, or the statement was, show that the normal line through a point x naught, y naught on the circle passes through the origin. Well, that's our normal line through that point. And we're just trying to show that the origin satisfies this equation, right? If you plug in 0 for x and 0 for y, that point is on the line. And the way you show a point on the line is by plugging in that point and making sure that you get equality. So I plugged in 0 for y and 0 for x. I got 0 minus y naught on the left. I got y naught over x naught times 0 minus x naught on the right. And then the left-hand side was negative y naught, and the right-hand side was also negative y naught. So yeah, 0, 0 is a point that's on this line. Kind of a strange question. I just wish there were more like actual numbers. That would make it a little more approachable. I know that's not, I mean, often in calculus, there's not a lot of numbers, there's a lot of functions, but problems like that, it seems like you get some functions. Sure, we should do this one. Yeah, okay. All right. So use implicit to find the derivative and the second derivative of x cubed plus y cubed plus 3xy equal to 6. And then find the equation of the normal line. Again, why? I don't know. Okay, so let's find the first derivative. So we're starting with x cubed plus y cubed plus, I'm going to think of this as 3x times y equal to 6. differentiating with respect to x, we have 3x squared plus 3y squared times dy dx, or y prime, plus product rule, 3 times y plus 3x times y prime equal to 0. Yeah, interesting. We're going to solve for y prime. So keep these things on the same side. So we have 3y squared y prime plus 3x times y prime equal to negative 3x squared minus 3y. Factor out the y prime. You might also divide both sides by 3, right? It'd be totally valid to cancel a 3 on both sides since everything is multiplied by 3. It's not always or often going to be true, but it is true here. So let's write this as y prime times y squared plus x equal to negative x squared minus y. Just dividing both sides by 3 and also factoring out on the left. Then y prime is going to equal negative x squared minus y over y squared plus x. Second, and we'll come back to the normal line in here. For the second derivative, so there's actually a couple ways to approach the second derivative of an implicit thing. Here's probably the most seemingly straightforward way, is just to use the quotient rule. So we're going to say the second derivative here is quotient rule, the bottom, y squared plus x, times the derivative of the top, negative 2x minus the derivative of y is y prime. Minus the top, negative x squared minus y, times the derivative of the bottom, which is 2y times y prime plus 1, all divided by the denominator squared. And then this is an excellent time to read the question again. You may write d squared y dx squared, the second derivative, in terms of x, y, and dy dx. That is a gift. Because if it were me asking this question, I would have said your answer should be in terms of x and y. Meaning for each y prime, you then have to plug back in this garbage up here. But he is saying you don't have to do that. So that's, again, a really, really, really important reason to make sure you read the question carefully, right? He is saying, oh yeah, you can write your second derivative in terms of x, y, and y prime. You can leave all those things in there. We're done. Yeah, sorry. I keep pointing to a thing, yes. It says, yeah, you can write d squared y dx squared in terms of x, y, and dy dx. Which y prime is dy dx. So that's generous, I would say. Definitely make sure you read for that if you're being asked to find a second derivative implicitly. If you can leave it in terms of x, y, and dy dx or y prime, you should, right? You don't want to do more work than you need to. I guess let's skip the last part of this question. I think we did enough normal line stuff already. Let's move on to the next question. Which looked a lot more interesting. Somewhere in my notes over here, yeah. Oh, I do like this. I like both these questions. So here's a question that is not written well, but we definitely know what it means. Show that the derivative tangent is equal to secant squared. So what are they asking you to do here that they didn't really spell out? They're asking you to write tangent as a quotient and then use the quotient. So if you see something like this that says show a derivative is equal to this, it's not just like, well, I know the derivative tangent is secant squared. They're asking me to do some sort of work. They're not asking you to use the limit definition. Right? We never talked about the limit definition of the derivative of tangent. We did for sine and cosine, but not for tangent or cotangent or cosecant or secant. So this question, I'd be willing to bet on your exam it'll be secant or cosecant, maybe cotangent. But I imagine this is going to show up. It's going to be one of those four functions: tangent, cotangent, secant, or cosecant. And your first step is going to be to say, okay, the derivative of tangent, or whatever your function is, write it as a fraction, whatever over whatever. For tangent, it's sine over cosine. It's probably going to be tangent or cotangent because that one requires a trig identity as well. For secant, it'd be 1 over cosine. For cosecant, 1 over sine, so on and so on. So we're going to write this as 1. Well, we're going to take the derivative using the quotient rule, right? So it's going to be, what is it going to be? Let's see. What's the derivative? Oh, there's a, so I'll say something. Yeah, let's see. Let's get remember how to do this. That's the bottom times the derivative of the top, which is also cosine, minus the top times the derivative of the bottom, which is negative sine, all divided by cosine squared. And although we took the derivative, we haven't finished the problem because we didn't show it's equal to secant squared. Now, if you wanted to be, if you had limited time, you might just write equal secant squared, and they might buy it. I would probably show at least one more step. If you're trying to show this as fast as possible without showing all the work, I might write equals 1 over cosine squared x, which you know is going to equal secant squared x. But I think the step they want you to show before you get there is to say that, oh yeah, my top part there is cosine times cosine plus sine times sine. But I think they would buy it if you didn't write that part. They'd be like, yeah, they saw that was cosine squared plus sine squared, which is 1 over cosine squared. But then that's equal to secant squared. That's how you're meant to do this problem. There are other ways of doing this problem that you're not meant to do it any other way. This is how they mean for you to do this problem. So do it that way. If it was cotangent, I'll just point out if it was cotangent, it's similar, but when you do the derivative of cotangent x, which is the derivative of cosine x over sine x, this one I would be careful to make sure you showed all the steps. Bottom times derivative of the top minus top times the derivative of the bottom, all over the bottom squared. If I was trying to skip a step, what would I write next? I wouldn't write, so actually, other question. What is the derivative of cotangent of x? Negative, right, negative cosecant squared. So the derivative of cotangent of x is negative cosecant squared of x. So if you wanted to skip the step here, the second to last step, I think, not that, should be writing that it's equal to negative 1 over sine squared. But then the step that people kind of get caught up on here is saying, okay, that's negative sine squared minus cosine squared all over sine squared. And then they can factor out the negative 1 from the top and say it's really negative 1 times sine squared plus cosine squared, which is then just negative 1 over sine squared, which is then negative cosine squared. So you can probably get away with showing a little less work there, just make sure you're careful. All right. Last one we'll do today, and then on Thursday we'll do more of this probably, because other people have a test on Friday. So the derivative of x to the x, oh man, written in the cruelest way possible. So kind of like, well, actually a lot like the terrible problem we done in the other test that was like something times something over something times something. And we use logarithmic differentiation, even though we didn't have to. Here you have to. Okay, technically not true. No, really technically not true. Okay, so I will point out there are 2 ways to do this problem. Here's the way I would recommend doing it. I would recommend, if you think you're going to use logarithmic differentiation, you have to write it as an equation. You have to write y equals whatever you're trying to take the derivative of. So we're going to say, great, y equals x to the x. Take the natural log of both sides so that we can bring down that x and write it as natural log of y equal to x times natural log of x. Differentiate both sides. 1 over y times y prime equals product rule on this side. 1 times natural log of x plus x times the derivative of the natural log of x is 1 over x. Solve for y prime, so y prime is equal to y times, do simplify this because it's easy, natural log of x plus 1. Finally, replace y with x to the x. So y prime equals x to the x times natural log of x plus 1. I will point out, because some of you might prefer and just find it easier, you can do this a different way. You don't have to use logarithmic differentiation here. You can say, I'm going to think of this as the derivative of e to the natural log of x to the x. That is also an option. If you have an exponential thing where your base and your exponent both have variables, instead of doing logarithmic, which is what I would recommend, you can say, well, write it as e to the natural log of whatever my function is. And then bring the x down in front of the log. So that's going to be the derivative of e to the x times natural log of x. And then you know how to differentiate e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of that stuff, which is going to be product rule, 1 times natural log of x plus x times 1 over x. Surprise, surprise, it's showing up again. Not a surprise. And then you could leave it like that, or you could simplify it. Now, one thing I will say, I think if you do it this way, you should not leave your answer as e to the x natural log of x times natural log of x plus 1. You should say, oh wait, I know that e to the natural log of e to the x natural log of x is equal to x to the x. So you rewrite this as, sorry, I know you can't see that. Close. You should write that as x to the x times natural log of x plus 1. All right, we should stop because I'm running out of battery and it's time. I'm going to unplug this and plug this in so I can not run out of battery. Cool. Sorry, I know. Sorry, it's gone. There you go. All right. So good luck on your test tomorrow. For those of you who have a test on Friday, good luck on your test on Friday. I'll see you before the. Oh, I forgot to handle the shoot. I'm sorry. Totally forgot to make sure you sign this on your way out, or yeah, sign on your way out, please. Sorry, I totally messed around and totally forgot.